Welcome to one more video on Schmitt triggers. So it's a advanced version, and we are seeing the simulations of this Schmitt trigger also in this video. Now, in the previous video, we have seen the non-inverting Schmitt trigger. Okay, inverting Schmitt trigger. Now we should see the non-inverting Schmitt trigger. As you can see now, the input voltage is applied to the non-inverting terminal. The reference voltage is connected to the inverting terminal of the op-amp. Now, this is what the transfer characteristics of this non-inverting Schmitt trigger. As you can see now, if the input voltage goes below VTL, the output makes a transition from plus Vsat to minus Vsat. If the input voltage goes above VTH, it makes a transition from minus Vsat to plus Vsat. Now the V reference is applied to the inverting terminal, and using the superposition theorem, we can write the voltage at V plus due to the input voltage as well as the output voltage. So using this equation, and of course we should try to obtain the expression for the threshold voltages, that is VTL and VTH. So we know that the voltage at the non-inverting terminal using superposition theorem can be written as V0 into R1 by R1 plus R2 plus Vin into R2 by R1 plus R2, which is using this circuit diagram. So be careful that R1, R2s are as per the circuit diagram. If you interest in the resistances, then the equation will change here. Assuming that the reference voltage is applied to the inverting terminal, so V minus is V reference. So we can obtain the expression for V plus. So when the output voltage is plus Vsat, so because output can be only in plus Vsat or minus Vsat, if the output voltage is plus Vsat, the V plus happens to be this voltage, meaning the output voltage, if it is in plus Vsat, it can come from plus Vsat to minus Vsat only when the input voltage goes below VTL. So that's what is written here. V0 will change from plus Vsat to minus Vsat when Vin just goes below VTL. This will happen when V plus is less than V minus. That is, at V plus should go below V reference. When the input voltage is varying, so there is a possibility that this input voltage may go less than VTL. When it goes less than VTL, the output makes a transition from plus Vsat to minus Vsat. So substituting V plus as V reference and V in as the VTL, because this lower threshold voltage what we are finding is for the input. So substituting V plus as V reference in this equation and V in as VTL, we get the expression as VTL is equal to minus Vsat R1 by R2 plus V reference into 1 plus R1 by R2. So this is a very simple rearrangement you have to make in this expression by substituting V plus and V in as given over here. So this is the VTL expression. Similarly, we can get the expression for VTH, which will happen when the output voltage is minus Vsat. If the output has to change from minus Vsat to plus Vsat, the input voltage should exceed VTH. That's what is written over here. The output is at minus Vsat. The output V0 will change from minus Vsat to plus Vsat when Vin just exceeds VTH. This will happen when V plus is more than V minus, that is V plus should be more than V reference. Substituting V plus as V reference and the corresponding input voltage as the higher threshold voltage, and rearranging the terms appropriately, we get the expression for VTH as Vsat into R1 by R2 plus V reference into the expression. Now, using this expression of VTH and VTL as given here, and we can know the hysteresis voltage, which is nothing but VTH minus VTL. This will be given by the expression. Now you are actually subtracting VTH minus VT. So when you actually subtract the V reference, which is in both the cases it is plus, if you want to cancel out, these will be get added up. So that's why you have 2 Vsat R1 by R2. When you actually add this VTL and VTH, we get this VCATs get cancelled. So we have 2 V reference into 1 plus R1 by R2. Now here you can see in the previous example where we didn't had we considered the non-inverting Schmitt trigger where we didn't have the V reference. So So this is, if you ground it, the UTL and the VTL and VTH are magnitude by same. We can by applying the reference voltage, we can make the VTH magnitude different from VTL magnitude. Now you can see it is 3 volt, this is minus 2 volt, here it is 8, here it is 6, here it is minus 2, here it is minus 4. Now care should be taken that while considering the specifications, the higher threshold voltage should be always more than the lower threshold voltage. Now you can see we have both positive, both negative, one can be zero. So this can be achieved by changing the reference voltage, and of course we have to assume one resistor and we can get the resistance of the second one. So this is what is specification. We are assuming the Vsat to be plus 5 minus 5, and the R1 R2s are found out to be 1k and 2k, and the reference voltage should be 0.33, so that we get a VTH as 3 volt and VTL as minus 2 volts. And we can also do one more design where the specification is given in the form of R1 R2. We have been of course the value of so these are all given here. So we are assuming a reference voltage of 1 volt, VCC as plus or minus 5 volts. This is actually plus or minus, not only minus, not only plus, it is both VCC and minus VC, it is plus 5 and minus 5. If we are using these resistance of R1 R2, we reference with this much supply voltage, the VTH will be 4.93 and VTL is minus 2.32. Now you can see here we have one positive, one negative. In the second example, we have both as negative voltage. It is also possible to have a reference voltage which is negative. So okay, these VTH, VTL are calculated using this equation for the VTH and VTL. So let us try to find out, let us verify the non-inverting Schmitt trigger by LT spice simulation. Let us consider the simulation of the first example where we are supposed to get a VTH of 3 volt and VTL of minus 2 volt. The VCC assumed is plus or minus 5 volt, and we are estimating the value of R1. Of course, to estimate R1, R2 and V reference, we are supposed to assume the value of R1 because we have only one equation and two unknowns. So the R1 is 1 kilo ohms assumed, and R2 can be evaluated as 2 kilo ohms, and the V reference evaluated is 0.33 volts. So let us go to simulation, try to use these values, and then try to measure the VTL and VTH. So we have this is actually R1. So R2 calculated is actually 2 kilo ohms as per the design, and the V reference is I think V reference is 1 volt, because we had V reference is 0.33. So let me change that V reference to 0.33 volts. It is now 0.33 volts. 0.33, and we have a reference, okay, supply voltage of 5, and we have this also as 5 volts. And no need to apply negative 5 volts because this polarity is already negative here. Now we are applying R1 is equal to 1k, R2 is equal to 2k, and so don't get confused with this. So let me make this R1 R2 so that we don't have any confusion. So this is R1. This is as per the circuit diagram on the presentation and in the simulation. Now this is fine. R1 is equal to 1k, R2 is equal to 2k, and we are applying a sine wave voltage of 10 volt peak, and let us try to simulate this now. Now you can see we are having this output voltage being simulated. Now you can see this is the transition. The output is making a transition from minus Vsat to plus Vsat and plus Vsat to minus Vsat. You can also see what the reference voltage, the output voltage. Output voltage was supposed to be 5 volt, it is 4.2. So this is plus Vsat. The minus Vsat is supposed to be minus 5, it is minus 4.42. So let us try to verify what is the VTH and VTL. We know that the VTL is that voltage where the output makes a transition from high to low. So this is high, this is low. So let me just trace at what input voltage this happens. So here This is the input voltage at which the output is making a transition from plus Vsat to minus Vsat, which are supposed to be minus 1.41. But according to our design, so we are supposed to get a VTL of minus 2 volt. So we are actually getting minus 1.4 something. So this difference is there because the Vsat what we have is not 5 and minus Vsat what we have is not minus 5. So this, because of this difference, the VTL and VTH is slightly deviating. But if you substitute the corresponding value of VTH and VTL, we'll exactly get the plus Vsat and minus Vsat. If you appropriately substitute as per the actual values, we'll certainly get the proper values of VTL and VTH. Care should be taken. So while actually calculating VTL or VTH, we have to actually move the plot on the input graph, and we have to try to find out at what input voltage output starts making a transition from plus Vsat to minus Vsat. In this case, it is minus 1.4, which is the VTL. We can simultaneously find what is VTH. So to find VTH, let me just go back and try to find out where it is making a transition from. Now let us see, this is the input voltage. Now you can see this is the input voltage where the output is making a transition from minus Vsat to plus Vsat. The corresponding input voltage is 2.41. So actually we expected a VTH of I think VTH of plus 3 volt. So we are not getting exactly plus 3 volt because the plus Vsat is not exactly 5 and minus Vsat is not exactly 5. So this is the actual VTH and the VTL was coming out to be minus 1.4. We can also change the axis here from this to the input voltage, which is nothing but V of N004, because this is the input voltage. So if you replace that by the axis and the y-axis, sorry, x-axis by time to this, we'll actually get the transfer. Now you can see this is the transfer characteristics. So it is surprising to see it is not coming straight away. So this is actually VTH and this is VTL. You can see now this is VTL. So the corresponding output, this is actually, so you can just move it on the output line. You can see, you can just move it on the output line. So this is VTL, which is actually 1.4. This is horizontal. So this is the input voltage at which output makes a transition, and the corresponding, this is VT. This is actually VTH. VTH is plus 2.4 and VTL is minus 1.4. Minus 1.4. So this way we can actually get the transfer characteristics. Now you can see this is not a straight one as it was there in the slides. In the slides you can see it's a straight one. So this, you can still get a straighter one if you reduce the frequency of the input. So let me reduce the frequency of the input and come back and see the simulations. So here the frequency is something like 1 kilohertz. Let me make it 100 hertz and try to get the same thing. So let me just simulate up to a larger time. So let me make it 50 milliseconds and you run the. Now you can see it is better. Now you can see it is much more sharper because the slew rate problem is going to have slew rate of the op amp. Now it is not too much of a slant. Now we can, of course, the UTP LTPs will never change, but you can see you're getting a proper waveform. While measuring VTH, we need to measure at the point where it is making a transition from this to from minus Vsat to plus Vsat, whereas VTL is from plus Vsat to minus Vsat. So you can just move it here. You can just move such that I can move it on the input line. So this is, you can actually see the corresponding voltages. This is, you can also see that X and Y axis settings. So this is your x-axis